And so we're continuing in that vein. We talked about speed before. Okay, so speed is, let's see, kilometers per hour. So speed is how far you went and how long it took you to get that distance. So speed is actually distance before divided by time, right? And I think probably maybe Friday or Monday, I'll go ahead and give you a copy of what, for your unit exam in physics, the sheet that the equations are going to look like. Like, oh, okay, so I'll have that. So that will remind me. Okay. So speed is distance divided by time. Now, before I go on to talk about velocity and acceleration, I want to introduce you to something that you're going to see coming up. There are Greek letters, you know, like the Phi, Theta, Kappa. Those are Greek letters. One Greek letter is delta, and there's an upper and a lowercase delta. But it's uppercase delta is a triangle. So anytime you see this triangle, that's the Greek letter delta, and that means change in. And you're going to see it here in a minute, but I just thought I would introduce it here. Change in. So sometimes for speed, instead of saying distance divided by time, we'll say speed is equal to change in distance, how far you went, divided by change in time, how long it took you to get there. So speed and velocity, sometimes we use them interchangeably, but there's a little bit of a difference. All it is that velocity is speed plus direction. That's it. Velocity equals speed, how fast you're going, plus direction. What direction you're going. Okay. So, for example, if we say that a car's speed is 45 miles per hour, now it's funny because I see that mph, and that's fine because we all know mph is miles per hour. But I really am kind of liking it, instead of writing it like that, what you see in the parentheses, 45 miles per hour. In fact, while we're at it, I really like to go ahead and say, put this like in the numerator and this in the denominator. I can rewrite that and say that's 45 miles per 1 hour. It's all the same. Okay. But units, miles and hours, they actually kind of have the word problem. So anyway, so if we give the speed and the direction, then we have velocity. So if we go ahead and say that same car is 1.5 miles per hour, but it's going in a direction northeast, bada boom, we have velocity. That's all it is. That's it. In physics, it works well to use these things called vectors, and all vectors are arrows. So this is a vector. Okay. Notice that, well, it might be intuitive like you think. You start it at the tip, start at the base of the arrow and go to the tip of the arrow. So it gives you direction. The other cool thing about vectors is the length of the arrow gives you magnitude. So which one, this is A and this is B, which one, if these are velocities, which one's traveling faster, A or B? A is traveling faster because the arrow is longer. That's it. It's kind of fun because then you can kind of cut them out, and I've done this before in physics class, and you kind of put all the little bases together and you can get a resultant because they all kind of work on each other. Okay, so this would be going what? Kind of northeast-ish, and this would be going west. Okay, and the length, to me, this length looks kind of like this length, similar, although you know there's optical illusion things. You know what they are. But these might be the same speed but different directions, so their velocities are different. This also, and this is my try to get a curve. It's a circle. It's not a circle. But anytime you are doing this, our dog is kind of But anytime you are doing this, you are changing direction. Okay, like this, a gentle curve or sharp curve, you're changing direction. So even if this person is, this person's changing direction. If you hold that thought. So we have speed and we have velocity. Velocity is the high level of speed. So now we have acceleration. So change in, I'm going to use delta. So change in velocity, acceleration is change in velocity. Acceleration is change in velocity divided by the time over which that change occurs. So acceleration, the variable for acceleration is A. In physical science, we do a lot of, we don't want to write the word acceleration, so we put in a variable. So A is acceleration. And to understand the acceleration objects undergoing, what we do is we get the change in velocity, and I didn't, what's the symbol for velocity? Change in velocity divided by the change in, I'll put the letter T for time. Too bad. Now, something is accelerating then if its velocity is changing. Velocity, though, remember that velocity has two components. It has speed and direction. So if you're changing either one of these two things, acceleration. Now, we're used to using the term acceleration a lot. In fact, I have an example up here. This car is going from, let's see, well, he didn't start at 0, did he? This car in this figure started at 10 kilometers per hour. And in 1 second, now it's going 20 kilometers per hour. It's accelerating. So we can actually, let me kind of see if my pen works today. Underneath there, I'm going to do, for this time segment, the time segment 1 second, I can knock out acceleration is equal to the change in velocity. So does this look right to you? It increased 10 kilometers per hour. The change in velocity, which is 10 kilometers per hour, and the time over which that change occurred was 1 second. Oh, darn it. Something like that. And I can divide 10 by 1. And so my acceleration there is, got to keep my units. It's going to be kind of weird units. I'm going to have to keep my kilometers and hours per hours and seconds here. These seconds are going to go in the bottom or the denominator. Oh my gosh, I made that big. Is that bizarre? That's never happened. Well, that's to my benefit. So those units are going to go in the denominator. So the answer is going to be, oh, but I lost my pen. Uh-oh. It's going to be 10, and units are going to be kilometers per hour. And then also in the denominator, sorry about my pen. I think I just need to buy a new one. I just like banged it up early in its life with me. Kilometers per hour, and also in the denominator, I'm going to go ahead and put seconds. So that's 10 kilometers per hour and also seconds. So that's the acceleration for that time interval. So let's see what the car does next. Well, actually, we have a different problem here. So here we have a different time interval at 2 seconds. He was clocked, or he or she was clocked at going 30 kilometers per hour. And now they stopped. So over here, acceleration, let me try this. I'll lay it flat, see if I have a fighting chance. So here, oh, there we go, that's better. Let's see. So acceleration is the change in velocity. Now, I'm going to go ahead and we'll talk about this more, but actually it's a negative 30 kilometers per hour. Okay. Change in velocity, negative 30 kilometers. Ooh, that's much better, per hour. What was the time interval over which the change occurred? 1 second. Again, the math's pretty easy. 1 second. Okay, so I'm looking at 30 kilometers per hour, or 30 kilometers per hour, and also in the denominator are seconds. So 30 kilometers per hour seconds in the bottom. Oops, better carry along my negative sign. So negative, you know, means it's slowing down. So these are, we call it deceleration, but it's like negative acceleration. So I kind of threw this up here. We aren't in this class going to calculate any sort of acceleration, but if this car was driving 30 kilometers per hour, which would be kind of dangerous depending upon how tight that circle is, to scale, it was kind of scary. But anyway, if they're driving at constant speed, but if they're changing direction, then they're changing velocity, which means they're accelerating. A good example of this, and we'll talk about this in astronomy, is this is my sun. Of course, the sun is just a beautiful star, G-type star. And this is one of my planets. This could be the Earth, or this could be Mercury, or something like that. I've drawn it off center on purpose because the sun's off center of the planets as they orbit. But the fact that they actually change direction means that planets are always accelerating, even if they're moving at a constant speed. Okay. Well, a minute ago, we came up with the change in velocity just by kind of eyeballing it. Okay, change in velocity for the first scenario was 10 kilometers per hour. The change in velocity for the second scenario was negative 30. But actually, what you really should do, anytime you see a delta, of course that means change in, you always go with whatever it is in the final state or the final whatever, minus the initial. That's just what we do in science, and it works out great. So with that said, I can kind of expand this delta velocity, change in velocity, and we're looking at, we'll put a subscript f there between the final velocity, and from that we subtract the initial velocity. Delta time, we can take the final time, it's always final minus initial, final time minus the initial time. That's just what we do. We just kind of apply that. By the way, I think we'll be doing some problems like this maybe. But if you apply this final velocity minus initial velocity, if you were to apply it to problems that we just did, for instance, with that deceleration, you would get the final velocity is 0. The initial velocity was 30. So 0 minus 30 is negative 30, which is actually what we learned, negative 30 kilometers per hour. So it's all kind of cool. Anytime you see this little bar in math always means average. Okay. The opposite or kind of in contrast to average would be instantaneous, and we're not doing instantaneous. There are other ways to massage instantaneous acceleration, instantaneous velocity. We're not going to worry, we're going average, which is a good thing. Okay. So the average acceleration, how much faster, we're going to kind of just deal with acceleration as something's going in a straight line like that car. The average acceleration is equal to whatever the velocity is changing, increasing or decreasing, divided by the time over which that change occurs. All right. So I brought my calculator, so I haven't done these recently. And so you guys can take a look at them, and I'm going to kind of do it up here on the board. Now, if I was doing this for homework, I'd probably try to draw a car. And I might go ahead and try to draw a car. My cars look really sad, but it's a way of stalling. And I'm not very artistic, although I do admire people who are. One of the things I told you for working in science problems that works real well is to draw a picture. So, car travels due north, so I'm going to be going due north, beginning from rest. So, oh my goodness, have to drive a sideway car. No, I'm not going to do that. So, this is my car. Oh my gosh. And it's going to go due north. Doesn't have any wheels on it. Okay. Beginning from rest. So, over here, at the bottom, I'm going to put V sub 0, or V sub I, excuse me, initial is equal to 0, and units are going to be meters per second. In the 3.4 seconds, so I'm going to kind of put my car up here because that's the kind of the end of this problem. That's the segment of interest. Okay, so I'm going to put the time, little t, the delta t, I guess I should put delta t, change in time is 3.4 seconds. Okay, and now after 3.4 seconds, the v sub f, the final velocity, is 15 meters per second. It's like, and this is where sometimes students work these problems and they're like, I don't need a picture, I don't even need to write it down. Well, at least you need to write it down, how you get your problem, you get your answer. But you don't have to belabor it. On your test, when you go to do the physics test, you will have this where I remind you that acceleration is change in velocity divided by change in time. And if we just kind of go quick and dirty to work the problem, not worry about the v sub f minus v sub I, since v sub I is 0, what's the change in velocity? 15, very good. And we're going to make sure we bring the units along with it, so 15 meters per second. Cool. What's the change in time? 3.4 seconds. I brought my calculator. If you brought yours, grab it and plug her in. One of the things, a big thing, well, it's kind of a big thing in science is how do we round this? And I'm not going to belabor it too much, but do you see where I have 2 digits in both of these? I'm going to give my answer 2 digits. So don't get crazy with the rounding, but that's actually correct this time. So 5 by 15, divided by 4, okay, 4.4. So I'm going to go with my first 2 digits, which is 4.4. And then what would those units be? Meters per second. But I need one more unit in there. Yep, meters per second, also in the bottom. Yep, 4.4 meters per second squared. Yep. Boy, it works. This pen works so much better when I laid that down. Oh, thank goodness. Any questions about that? So what 4.4 meters per second or meters per second squared means is for every second this car goes, if it keeps up this pace of hit the F pedal, it's going to go faster and faster. For every 1 second, it's going to go faster 4.4 meters per second. Take a look at that here in a minute. Cool. Let's do another one. The car is traveling due west. All right, so here's my car. It's going west. Oh my goodness gracious. It's going west now. And the car is traveling due west at 29 meters per second. Oh, the car comes to a full stop. So here I'm going to make it, this one over here on the right, I'm going to make that
my velocity 0. My v sub 0, oh sorry, 0 and I means the same thing. My v sub I, my initial velocity, that is 29 meters per second. And here, it's going to come to a full stop. So what's its velocity at a full stop? What do you think? 0. Yep. I'll go ahead and put 0 meters per second. And it said that it was able to accomplish this deceleration in time. So I'll put delta t, change in time, is 10.2 seconds. So this time, if it's okay with you, I do want to kind of pull out my delta v, my change in velocity is v sub f minus v sub I. So plugging in from my picture, oops, go back. Plugging in from my picture, my final velocity was what? 0. 0 meters per second. My initial velocity was 29 meters per second. So what's that equal to? Negative 29. So that was my change in velocity. And again, that kind of goes back to the problem we worked a minute ago where we said, it's decelerating. Just put a negative sign. So now, how do I finish the problem? What's acceleration then? I'll go ahead and answer. You guys know this. The change in acceleration we said was negative 29 meters per second. The change in time was that 10.2 seconds. Now, when we go to round our answer, it's going to be the fewest. So does this make sense to you? I have 2 digits up here, and actually that 0 counts. So I actually have 3 digits here, but I gotta go with the fewest, which is 2. It's a little different in addition to subtracting, but I'm not going to break that. 29 divided by 10.2. I got 2.843137255. So I'm going to take the first 2 digits, which gives me 2.8. And what would the units be? Yep, meters per second squared, or meters per second per second. Cool. That's easy. Yeah, and I apologize, you guys don't have these, but here they are. So on the pages 49 and 50, there are 2 problems that you need to do. 12 and 14. Any questions about how to find, not that I would go right to the answers, but how to find the answers in Canvas? I think the Shipman textbook that we're using, I think that, like most textbooks, has the odd ones in the back, I want to say, too. So. Okay. Onward and upward. So actually, I think this is right. That's about all the math I want to do in chapter 2. But I do want to. Well, no, it's not all math. But these now are kind of concepts. These are everyday concepts that Sir Isaac Newton, was it 1700s, with the whole apple bomb, same sort of thing, came up with some concept of gravity. You know, it started that whole thought process of what we know about gravity. And then he also came up with these laws of motion, 3 laws of motion. So his first law of motion, and they kind of make sense, but his first law of motion says that if you have something at rest, it's going to stay at rest unless it's acted upon by some other force. And that kind of goes back to the other day I kind of said, if something relocates from position A to position B, the only way it can move is some force is applied. So left on its own, everything is going to stay where it's at. This is why we should never, if you know you have something to do, never come home and sit down. Because you're just like, that's it. But, okay. This also says, though, that if something is in motion, it's going to keep that same motion forever. unless acted upon by an outside force, which is really exciting. So we talked the other day, if I scoot something along the table, I think you told me that it will come to a stop. You said there's friction involved, actually there's gravity involved. Those are two important forces that make that object come to rest. But if you go into outer space, oh, she's on a spaceship. She got room, and she's the only one. I think she needed it for 5. What is it? Gravity. Thank you. She did make it back. She didn't die. She didn't die that? Okay, thank you. So space movies like Gravity really, they take into consideration this idea that if you're in outer space, there's not friction or gravity, there kind of is, but there's not friction or gravity necessarily to kind of slow something down. So take that into consideration. So something will keep not only, it will keep constant velocity, which means the direction and speed will. So the example I have here is like Stonehenge, right? Those rocks, they've been there a while. Unless some force acts upon them, they'll probably be there a long while later. Here's one, this is fun, this little trick, where you have a stack of pennies. What happens if you jerk that paper out? It's nice if there's not a lot of friction between the pennies and the table or the paper. Why? Because they're standing still and they're just cool. Oops, this was my thing. This was the gravity movie. Now, this idea of something at rest, staying at rest unless you apply a force, or something in motion, keeping that same motion unless you apply a force, that's what we call the law of inertia. Newton's first law is called the law of inertia. So inertia, on the next slide, I want to kind of say, well, what is inertia? Well, inertia has to do with an object's mass and an object's motion. Okay. So here we have, I have a couple of scenarios, and of course we don't around here have these, but you see them in the movies where you go to ride mass transit and you have to hold on to something and all sorts of people, exciting, okay? But here we have this person on a bus and he's watching his cell phone, okay? This is before the bus starts, so he is at a zero velocity, okay? The bus starts to move, according to inertia or Newton's first law, he didn't get the memo. So he's still at rest, the bus moves and he falls backwards. Well, another scenario is that the bus has been going. The cool thing about inertia is that once you have motion, as long as that motion is constant, I'm trying to walk a constant speed here. I don't feel any extra force on it. Okay, but the minute that motion stops, I don't get the minute. The thing I'm writing in this case stops. I didn't get the message, so my inertia carries me forward. That makes sense. So in this second scenario, in between here, he's riding on the bus. The bus and him, let's look at this way. The bus and him are both going 20 miles an hour. In this scenario, the bus stops, but he continues to go 20 miles per hour. And that's what he's doing forward. Okay, so inertia is related to how fast you're going and then the mass you have. So here's an example. This is a generational picture here, where we have probably the parent pushing the grandparent and her kid. 3 generations. Okay. So in this case, the little kid over there that she got started has a certain amount of inertia related to that little child's mass and how fast she's swinging. Okay. This guy has a certain amount of inertia associated with his mass and how fast he's ultimately going to be swinging. But as you might imagine, to get that person to go from standstill, he's got a lot of inertia at standstill too, you know what I'm saying? So she has to push really hard. Once he's going, he's got a lot of inertia going. So this takes more effort to get this person to move, okay, but once they're moving, they have more inertia. A lot of inertia here, a lot of inertia there. This person has inertia. So Newton's second law of motion is actually an equation that we're going to come back to. Probably won't get to it today, but F is equal to ma. If I choose, sometimes I choose on your physics unit exam, if I ask you to explain Newton's 3 laws of motion for his second law, you can just say F is equal to ma. We do a lot in the physics and a little bit in chemistry of just putting an equation and just saying how these 3 quantities are related. What do you think F is? What does that stand for? Force. Yep. Force. And sometimes I like to think of it as force applied. It could be a push, pull, poke. The force applied will result in, what's A stand for? Acceleration. Yep. Related to the object that you're pushing or pulling, the value of M for that object. What's M? Mass. Yep. And it makes sense. Okay. Like for instance, if we were to go back to this one, if I apply the same force to the little girl or the guy, the one with the larger mass, same force, is going to have less acceleration. Does that make sense? Because these two multiplying together is equal to force. The lower mass with the same force is going to have a higher acceleration. All right. That's kind of what's shown here. I was like, what does this mean? By the way, gosh, it was years ago, maybe 10 years ago, that International Space Station was, I think, fixing the Hubble Space Telescope. And had to be a woman, right? Big deal. But anyway, she was up there and she released her gizmo, some sort of wrench or something. It's still in outer space as far as I know. Okay, there's a lot of space junk up there. But anyway. So as she lost her wrench, okay, notice that, actually this is Newton's 3rd law. For every action, there is an opposite equal reaction. So actually kind of the force from the hand made the astronaut accelerate this way, and then the wrench accelerate that way. Which one looks like it's going faster? This is where they separate. Wrench, and it kind of goes back to that this is a greater acceleration as the lower mass. Stronger the force, the greater acceleration. With the same force, the greater mass, that means that the acceleration has to go down. Because we kind of do it like this. Like if I'm over here, mass acceleration, as mass goes up, acceleration goes down. We'll call the product or the multiplying of those two is that constant. All right. So Newton's 3rd law, or wait, this is a little bit more of a 2nd law. Force is equal to mass times acceleration. So here we go. Oh, I know. So if your acceleration is 0, and acceleration is speed, change in speed and direction. So in other words, if your speed is constant and your direction is constant, you have no acceleration. This kind of goes back to what I was saying a minute ago. If you're cruising on a bus and that bus is going 30 miles per hour, as long as it goes 30 miles per hour, you can kind of have a free reign of walking around and not feeling any kind of net force because your acceleration is zero. And so there's a guy in a bus, here's the people in the elevator. That's why, have you guys been to, but gone to this is my Arch, St. Louis, take an elevator up. So the way elevators work is they go kind of, your stomach kind of goes in the beginning, but once they hit that fast speed, it's a fast speed, but it's constant. So change in speed, zero. Change in direction on that change. So if that's zero, acceleration zero. Okay, so here I have a guy. And he is pulling with the force. You see the whole vector thing, right? You can kind of see the direction that he's pulling by the red line, and the length of the red line says how much he's pulling. And certain mass m, and this is his net acceleration. So in this case, notice he got a friend, woman in a dress, who's pulling a box. How do you wear a dress to pull a box? But anyway. See, they're pulling together. Now instead of just one F, they have two F because they got the force. And same mass, and this will actually double their acceleration. So you actually see the blue line back to acceleration. But now we're back to the guy who must have made the girl mad. Anyway, so he's back to pulling just one force, and he doubled his mass. And so, of course, increase mass, that's going to lower your acceleration. So actually you can see that acceleration is just half, or a over 2 of what. Okay, Newton's third law of motion. This is the one where I like to tease if you have siblings. You know, we have 3 kids, and growing up, the line was, dude, if you poke her, she's going to poke you back. So this is where for every action there is an opposite and equal reaction. Okay? Newton's third law. So objects that apparently seem to be independent of one another, if they're in contact with one another, okay, they can be exerting a force on each other. So anytime, for instance, you push against a stationary object, we're applying a force. I can feel it. And if it's not moving, actually the object you're pushing on, just like this shows you, is applying a force back to you. It's an inanimate object. It's a wall. Okay? But we have these 2 forces with the same magnitude in opposite directions, which actually means nothing is going. So F1 is equal to F. Now, sometimes things do happen. So, for instance, here we have a racket hitting a tennis ball. So think of the area of contact, okay? And think of moving the racket and actually the ball coming to it. Okay? But you end up with where they join a force. Skateboarding, a force and a force. We apply a force in this direction to go this way, and the force in that direction not only gets us this way, but it gets your skateboard that way. Okay. Here's one. I like the little stick person, right, on a boat. And that doesn't look very safe, but when he or she steps off, applying a force that way, the person can go this way, and the boat goes back. I think I mentioned this, like the whole how much something weighs versus how much mass something has. And we kind of use mass and weight interchangeably, but they're really not interchangeable. As it turns out, mass, and we'll talk a little more about this in chemistry, but mass kind of goes back to like how many atoms you have going on there. Okay, weight actually goes to how much, kind of what planet you're on, okay? What your weight is, because weight goes back to how much that mass is attracted to the object you're standing on, which in this case is the Earth. If we stand on balance, that's kind of what we're gauging. So that's okay. So mass in that sense, does this make sense? The whole mass thing being the atoms, okay? Mass is what we say more fundamental. I have a picture coming up to show you that the mass, your mass on another planet, your mass on the moon, okay, whether it's a smaller planet or a bigger planet, of course the moon is smaller, your mass is going to be the same, but your weight's going to be different. So weight actually is a function of your mass, and like I said, the mass of the object that you're interacting with, whether it's the Earth, or the moon, or Mars, or an asteroid, planet X. So weight, we say, is kind of how heavy the object is, because, you know, it's like you're picking up your feet, you're fighting against gravity. If you're picking up your feet on the moon, gravity, right? The folks who were on the moon had to have like heavy moons, because otherwise they had issues. Ended up point C when they wanted to go to point B. Okay, so the larger the masses of the two objects, then the greater the force of gravity. It's funny to think that actually we think of objects like ourselves being pulled towards the gravity of the Earth, but the Earth is actually pulled towards us. So the influence of the Earth. Okay. Which reminds me, and I think this is one of those, you do such a great job. It's not Penn and Teller, but it's the ones that do the Mythbusters. The thing where if you get a bunch of people to jump off the Earth all at one time, will that have consequences to the rotation of the Earth or any consequences in the Earth? But it's still a pretty cool idea. So in a minute, you're going to see a mathematical equation of how Newton kind of describes mathematically gravity. So F there is the force of gravity. Looks pretty complicated. I'm not going to make you crunch any numbers, but we should kind of know what this seems like. It's pretty intuitive, I think. The big G is a constant. I kind of tease a constant in this universe. Could be a different constant in a different universe. But there's actually a value to go to G, and you can look it up. That's 6.67 times 10 to the negative 11. Units of G are newtons meters squared per kilogram squared. Well, the things that can change out are the M. So what does M stand for? Mass. So that M1 is the mass of maybe you, and M2 is the mass of the Earth. And then R is the distance between you. And notice we're going to square that. So intuitively, if you increase any of these things mathematically, M1 or M2, what effect does that have on F? It increases it. So increase any of your masses, the force of gravity increases. What if you, and you know, not look at that equation, but what if the farther the distance is between those two masses? What does that do to the force of gravity? If we can, you can actually kind of see mathematically, if you increase something that's already in the, what we call the denominator, it's going to decrease the force of gravity. Well, that's a good place to stop. So we'll pick up on next slide. This is Wednesday, on Friday. But don't forget we have lab tomorrow at 10. It's room 512. So to get to 512, we already know, you're going to go down this hallway, kind of take a sharp left, and then jag over. And then you'll be in building 500 then go kind of to the end of building 500. 512. Okay? And if you remember, bring your the sheets I gave you. That would be great. I'll have a few extras just in case.